Okay, we just spent some time going over electric charge basics. Now we're going to spend some time looking at electric force. What is the force that happens between two charges? You already know there has to be some kind of force between two charges. You've seen it when you see static cling, or when you can rub your hair on a balloon or something, and all of a sudden your hair standing up, because there is a force between those two things, between your hair and the balloon, and it's enough to lift your hair up. So there is a force between charge. We see this with our static charge. So here are the pieces. Okay. We've got the electric force is equal to Coulomb's constant times the quantity of Q1 times Q2 divided by R squared. Like the Newton's law of universal gravitation, this is an inverse square law. Okay, and you'll notice that we're no longer using mass to find force. When it comes to using electric force, we use this new thing called coulombs, which we started learning about with charge. So charge is what you need to measure electric force. All right, you're still going to end up with newtons no matter how you do it, but we don't think about the mass, we think about the amount of charge. Let's go ahead and let's do a bit of a practice with this. Actually, small aside real quick. Down here, Coulomb's law. This is called Coulomb's law, but it's not actually, was not first developed by Coulomb's law. It is from Cavendish as well. Cavendish is the gentleman who came up with the Cavendish experiment, which is what they used to determine the value of G. I want to say it didn't even happen in his lifetime, that he started it and the work had to be passed on to somebody else because he passed away. So he did this entire universal gravitation constant, and he also developed this law, but he never published. And so when Coulomb came along, he published, everyone kind of attributed it to him, and he's the guy who got all the credit. So, mathematically wise, guys, it's the exact works the same way as universal gravitation. You're just using you're using different values. Let's go ahead and ask a rather important question. What is greater, force of gravity or the electrostatic force? I'm not going to go full on into the numbers right now, but I will go ahead and we'll do it as an order of magnitude check, okay? So if we've got the force of gravity, just one second, fixing something, there we go. All right, the force of gravity is a gravitational constant times m1, m2 over r squared. So if for this experiment, for this kind of test to figure out which one's bigger, gravitational or electrostatic force, we're going to use an atom of hydrogen. It has one proton, one electron, and we're going to use this distance right down here at the bottom, 5.3 times 10 to the negative 11th. And right here are our mass and our charge. Like I said, I'm not going to plug everything in. We're just going to do an order of magnitude test to see what happens. Okay. So, one second. So, approximately speaking, if you've got gravitational constant is times 10 to the negative 11th. All right. That was... Okay. So I interrupted myself right there to go ahead and write down my constants. So universal gravitational constant is to an order of magnitude 10 to the negative 11th. The mass of an electron is an order of magnitude 10 to the negative 31st. Proton, order of magnitude, is 10 to the negative 27th. Okay. And our radius is 10 to the negative 11th. We're going to square that. Whoops, wrong place. Okay, so let's go ahead and work our way through this. If you are multiplying things with exponents, you can add the exponents. Actually, let's back ourselves up. Notice that this one's negative 11th and this one is negative 11th. What that means is that there's 1 up here, and I can cancel it with 1 down here. All right, so that leaves us with just this, this, and this. All right, so negative 37, negative 31, excuse me, plus negative 27, divided by 10 to the negative 11. That becomes negative 31 plus negative 27 is negative 58, 10 to the negative 11, and if you're narrowing that down, it becomes 10 to the negative 58 minus negative 11. So it becomes 10 to the negative 47. So whatever we're doing, if we're talking about the force of gravity, it is approximately 10 to the 40, something a 10 to the negative 47th newtons. Now let's do electrostatic force. I'm going to erase a whole bunch of stuff down at the bottom. Okay, so we cleared up some space. Now we'll do the same thing we just did. We'll do with electrostatic force. Now electrostatic force, the equation, that's one we just learned. K, charge 1, charge 2, Coulomb's constant times the product of the two charges divided by the distance squared. This becomes, okay, K is to the power, order of magnitude of 10 to the 9th. And we've got Q1 is 10 to the negative 19th. Q2 is 10 to the negative 19th. And we're dividing that by a separation of 10 to the negative 11th squared. All right, so math-wise, it's 10 to the 9 minus 19 minus 19 divided by, and if we square it, it's basically multiplying the exponents. So it's 10 to the negative 11th times 2. All right, 9 minus 19 is negative 10. Negative 10 plus negative 19 is negative 29. So it's 10 to the negative 29 divided by 10 to the negative 22. So 10 to the negative 29th minus negative 22 leaves us with 10, something on the order of magnitude of 10 to the negative 7th. So force, electrostatic force is approximately 10 to the negative 7th newtons, which makes the electrostatic force the clear winner. It is much, 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 much stronger than our gravitational force. So for homework tonight, you should be working on the electrostatic, the charge and electrostatic force problems that were at the front of the room. There will also be, there's a quest out there for you. And if you did not finish yesterday's gravitational field strength assignment, that needs to be done as well. There will be grades taken. Talk to you guys Monday.